Hey guys, this is going to be a video tutorial on using the program Tracker. So I've already got it opened up here, and how I added this video of this really good looking chemistry teacher is I went into import video and just selected the file. It's easiest if you just move the video that you're wanting to analyze to your desktop and then just adding it from there. Now, he's going to be throwing the ball up, so it'll help us if we rotate this video, because I took this on my iPad. So we go to Video, Filters, and we go to Rotate, then click Properties, and we want to rotate it like so. Now, in this video, we didn't establish a scale, so what I can do is you go up here and you click Create, or actually come up here to the little 10 and the plus. This is how you create a calibration stick. And what you're going to do is you should have had a meter stick in your video. But since we didn't, I'm going to make my units, which are completely arbitrary, I'm just going to make it 1 Dorch. Now, we're going to be throwing the ball up in the air, so we want to create a point mass. Okay, so that creates this right here, and you want to scrub until right when you release the ball. So it looks like right about here. Now, what you do is you push control, tap your mouse, push control and click, or shift and click, excuse me, shift click, and you get this little crosshair thing. Now you want to pick the same spot on the ball each time. Now the ball in our video, it's a little blurry, so I'm going to always just have my crosshairs on the top of the ball on its way up, and then the bottom of the ball on its way down. So you click, and then it jumps to the next frame for you. So I'm going to the top of the ball, or what I think is the ball, click, top of the ball, click, top, click, again. So it's reaching its max height, it's slowing down, and it almost hits the ceiling. It gets pretty close. And now it's stopped and it's starting its descent. And there she goes, coming back down. This part isn't the most fun, but it looks cool whenever you play it. So let's get all these clicked. And again, shift, and then just click. And we're back down. Okay. Let's give it one more. There we go. Now, it's also beneficial to set a coordinate system here. So you push your little axes button right here, and we can make it wherever we want. So I'm going to put it right here, even with where he's released the ball. So right about here. Okay, now if you play this back, it'll show all of your pretty cool. So let's crunch some data. Over here, this shows your position in X versus time. So this is your lateral movement of the ball. Not much going on here. What is really beneficial for us is your Y position versus time. If you look at that, you get a really nice parabolic curve, which is what we'd expect for constant velocity or constant acceleration. So what we're going to do is you're going to right-click the graph, and you're going to click Analyze. Alright, and it brings your graph up here. So now what we're going to do is we're going to fit this graph. Now, right now it's fitting it as a linear equation. We don't want that. We want a parabola. So it fits it into the at squared plus bt plus c, and it gives you your coefficients right here. So I am going to copy that equation right here. We've got y equals, let's see, it's negative 2.844 t squared, and then plus looks like 3.36 t, and then minus 0.244. So that's the equation that it spat out for me. Now what that is modeling is one of your kinematic equations. Okay, it gives you your x final, in this case our y final, equals 1/2 at squared plus v initial t plus x initial. So if we look at this, we set our coordinate system as 1 Dorch. So negative 2.844 Dorches equals 1/2 your acceleration. If we model this, the slope of our line should be the same as the slope of our kinematic equation. So if we solve for Dorches, in other words 1 Dorch, let's get our old calculadora out, acceleration is negative 9.8 meters per second squared. So if we solve for d, or 1 Dorch, let's see what we get. We go negative 9.8 divided by 2 for the times 1/2, and then also divided by negative 2.844. So that gives you 1 Dorch equals 1.7, we'll go with 1.73 or 723 meters. So if you figure 1.723 meters, let's convert that to how many feet. Well, 1 meter is 3.281 feet. So times 3.281, we get 1 Dorch equal to 5.65 feet. So we get him as roughly 5.5 feet tall, which is a pretty good approximation if you've ever stood near him. So that is what you'd want, because the most accurate data you are going to get from this program is your position versus time graph. You can also jump back here and look at your velocity versus time graph. Now, it's crunched the numbers and done the derivative of our position versus time graph, and so that's why you're starting to see a little bit more scattering in our velocity. It's still linear, as we'd expect, because our acceleration is constant, but it's just not the most accurate data that we can get. The most accurate data is the ones that we point and click and stuff like that. I've got a little point here that might be a little too high, or this point might be a little too low. But anyway, that is using Tracker to track an object's position using video analysis. Pretty cool stuff.